Okay, so today we're going to talk about how to learn on your own. All right, and this is basically self learning. Now, the question is, can you learn on your own? And the answer to that is simple. Yes, you can learn on your own, and it's actually extremely effective. There's this debate on how far can self learning take you? And based on my experience, I self taught myself a lot of my subjects. And the most the best thing that I'm proud of is that I self taught myself about computer science, mathematics, science. I was very interested in those things. And I aced all my subjects. And I was that kid who really didn't have to study before tests because I already knew much more than what the test required. I would always ace them. I would get like straight A's, nearly perfect scores on all tests, even on the ACTs, all fives on like the hardest math and physics AP tests, like Calc BC, Physics C and M, statistics, computer science A, all of that, and I didn't have to learn from a mentor or a teacher. I did it all by myself. And at that time, with the help of Khan Academy and the internet. And I got to a great school. I'm a University of Waterloo CS student in Canada. And, I'm doing pretty well, right? And I also won like a bunch of competitions related with coding, computer science, artificial intelligence, and I also made some products while working at a company that's related with artificial intelligence, military strategy, military training programs in South Korea. So I'm doing pretty well for myself, right? And although this whole how should I call this? This bragging is not intended to brag. It's stating hard facts about my achievements. I'm very proud of what I achieved. And although it was very hard, it's all worth it. And those are the heights that you can achieve with self-teaching, self-learning. And, I know that this might feel a little suspicious because there's not enough proof. It's just coming from a single guy who's just talking over the internet. But, if you take it with a grain of salt, and if you believe it, then at least self-teaching can get you somewhere, and it's a very effective way to learn things. And in college and, after high school, especially if you're going to do research and write papers, you have to self-learn. You have to be comfortable at doing things alone. And especially if you want to start a business, or especially if you want to be at the forefront in technology and start a tech company, you got to learn how to self-teach yourself, self-learn, because you're going to do things that no one has ever done before. And there's no textbook, there's no teacher, there's no mentor who can teach you directly about the things that you want to solve. You're on your own. And you got to really have a knack of collecting background knowledge that could be related to your problem and actually solve it. So self-learning, self-teaching is very, very important. And I'm going to, basically, this is a small lecture on how to self-learn effectively. And I'm just going to add some of my AI knowledge and give some evidence and experimental, academic experiments and results on, you know, on our experience in while training AI. Like, how does AI learn so well? Like, what techniques boost performance in AI, right? And this is a really, really interesting topic to connect to And there's a lot of great lessons that we can learn as humans, because, well, AI and humans, they're basically what? Learning agents. And techniques that we discovered that make AI learn really well and really fast can be equally applied to humans. And that's what I'm going to do exactly today. But 90% of the, sorry, 85% of the content, you'll know why I'm specifically mentioning 85%. 85% of the content that I'm going to provide in this lecture will be based on my personal knowledge and my personal philosophy and my personal experience. But 15% of the content will be some evidence related with artificial intelligence and the mathematical and statistical knickknacks of what it takes to learn effectively on your own. And just before we go into that, in a artificial intelligence language, self-learning is self-supervised learning, or you can even say unsupervised learning. It could also be related with reinforcement learning. If you're trying to say, I'm taking this test, and based on the test score, I would like to improve myself. Like that would be in the category of reinforcement learning. So I'm basically going to provide some evidence and academic knowledge on what we discovered in AI when it comes to unsupervised learning, self-supervised learning, and reinforcement learning. And basically compile some evidence that suggests these are the things that you should do in order to learn really effectively. So let's get straight into it. I wrote some notes, and let's just talk about, before we even self-learn, what should we prepare? How should we prepare ourselves? And these are some of the things, right? So you have all the time in the world. You have to think like that. And this is really important because you should not chase for time. You should never, ever rush yourself in learning. And this is especially true when it comes to self-learning. Part of self-learning is that you're committing yourself to learn knowledge without anyone's help. It's like a meditation, self-meditation. So you have to make sure that you have to have all the time in the world, and you have to give yourself a lot of room, infinite amount of room for you to explore, review, and ultimately compile the knowledge that you've learned into a single framework. And I'm going to explain that soon. So if you don't have the time in the world when you're learning a subject, you have to make time. You have to make enough time for you to learn that subject, get comfortable with it. And most of the time, this is going to be a lifelong endeavor. No one in the world is ever going to master mathematics within N number of years. There are still math professors around the world who are still learning about math, who are still studying this, philosophy, right? And, they get continuously better at it because subjects are never ending. There's no curriculum. It's like an ongoing topic that ever evolves. It gets better and better and better every time. So in reality, you should have all the time in the world, and you should just take your time and just treat learning as a lifelong journey. And by journey, I mean, don't really focus on the destination that you want to go to. Focus on the steps you're making right now. Just enjoy the journey. You also have to not feel anxious about yourself, all right? So no anxiety and self-doubt. Do not be suspicious about yourself. Don't say, oh, can I make it? Can I do this? Can I do that? Am I really capable? Am I smart enough to do this? Because what happens in self-learning is you get smarter as you do this, okay? It is bound to be that way if you do it properly. It's a method and technique that's important, not the talent and the skill that you already have. Children are stupid. Okay? Every child is stupid. You got to know that, all right? If you compare, like, I don't know, a child Einstein or a child Elon Musk to an adult, the adult's going to crush everyone, even the child Einstein. Because, well, children don't know better. Children don't have enough expertise, knowledge, experience, and the necessary skills that an adult has. The adult has practiced that for decades. What really happens is all children are like similar in talent, more or less. And then as they grow and as they like choose the correct methods or the wrong methods, the gap increases. And that's why as an adult, you got this adult Einstein and an adult Elon Musk versus like an adult average Joe, right? There's like that huge gap. And part of that is selecting the proper techniques, getting used to that proper skill level or getting used to that proper perspective and mindset on how to learn and how to navigate your way through this, ever-growing knowledge in the world. So do not self-doubt. You will get better every single day. And this is not a skill issue. Okay, this is not a talent issue. So you don't really have to worry about it. Okay? All right, so that's that. Now let's talk about how, to self-learn. And the best way is to pick a problem that interests you, the most, or that interests you, and solve it, on your own. You're going to do this infinitely many times. But the key is, although you can learn the background knowledge needed to solve this problem, do not look at solutions. Do not look at solutions, Solve it on your own. And this is very, 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 very difficult, And it's very rare for anyone to have solved even a single problem on their own, even as adults. And this is very surprising, especially if you're like a younger audience, like a teenager or even a child. It's very hard to do it. It's so hard that even most adults, have not yet solved even a single problem in their lives on their own. They asked for help, they looked for solutions, they copied solutions, they copied suboptimal solutions, and just kind of like, squeezed it into their own problem, like as if you're fitting like a square, you're fitting a round peg into a square hole. So it's very hard, but part of the difficulty is not about the actual level of difficulty. It's not like an enigma kind of a problem. Like, it's not like an enigma challenge. It's not like, people who are super smart can only do this. It's more about most people don't have the grit nor the patience to stick to one problem and keep doing it until they finally solve it. Because it takes about 6 months to solve a single problem on their own, even if you like keep thinking about the problem for 6 months straight and you like try and try and try. 6 months is also fast. Most of the time, it takes decades to solve that problem on your own. And it depends on the level of problem that you're solving. If you have a, quite simple problem that you want to solve on your own, like a high school math problem or a college math problem, you could be looking for like 3 months, probably a month, right, of, solving it on your own before you have this eureka moment. So it's very hard, right? Like it's unimaginable at this current day and age where, children are seemingly mastering calculus at the age of 6 in Korea, at least, right? That's basically unthinkable because, in the minds of Asian parents or Asian students, especially, like this is coming from my experience, we like to rush things. We like to say that, I speed run this subject, and that makes me therefore smart and talented and more capable. And I like to say that that's bullshit because you're not learning in depth and you're going to regret it for the rest of your lives. So that's why, all right? It's a cultural thing in Asia, especially in Korea. It's also a personal thing. No one realizes that actually spending 3 to 6 months in solving a single problem is good, is okay, and it's actually the right way to solve problems, and it's the right way to learn a subject really, really deeply. Um, so it's all of those things. But once you realize that, and once you believe that this is the right way, uh, I think anyone can do that. And we need more people, we need more talents who have actually done that. Okay? I promise you, it's like night and day when you just do this. Okay? You're gonna be at like another level than like any of your peers who have not done this. It's like that impactful, it's like that phenomenal. In my case, um, it was like I think I did solve one, all right, when I was a teenager. Um, but most of my life, it was more about like combining recipes that were already given and trying to apply it to a new domain, trying to apply it to like a new set of problems and test them out, right? And that's what I'm still doing. But that is not really close to ingenuity, basically trying to solve something completely new. So it's if I were a kid again, I would simply spend 6 months of my life to try and solve a single problem completely on my own without really looking into like the solutions and all that. So I do regret that. I have solved one and that made a phenomenal impact. It was a quadratic formula basically, right? So I didn't really look at the formula. I didn't know there was a formula. I did kind of take a glimpse at it, but I kind of derived it from the very beginning. Try to solve this out. Like, why do I need to do this, and what is the core thing in the quadratic equation? And like I kind of pondered about that for like a month or two, and then finally I kind of got that solution of the quadratic equation. And it wasn't like I think it wasn't the perfect solution. I think it was like close to it, and I looked at the solution and then I kind of, reflected and say, okay, where did I go wrong? What was wrong? And then kind of backtracked and then figured out the error and then kind of, mastered it. It was like the best feeling in terms of my academic journey. But I wish I'd done more. And I wish I held on to held on to solving harder problems for like longer periods of time. Because it's like, super effective. But luckily, I I did the same thing in programming. I basically programmed without looking at solutions because, copy and pasting code wasn't my thing. It never worked, and I was tired of fixing bugs and crashes. So I decided to just implement on my own, and I learned a ton while doing that, right? From drawing my own diagrams. I have a unique way to draw diagrams. It's like a combination of flowcharts and just literally writing and drawing like a bunch of these like architecture diagrams, explaining, annotating like what I need to do and what is the logic, add some math equations and formulas into it. And then I kind of like organize it into like a English version of like the logical flow of it. And then I code, right? So I have my own way of, building a plan and then executing it and minimize as much errors as possible that I have to fix. And that took me years. That took me years to figure out. That took me a bunch of mistakes. a bunch of like, trials and errors before I actually molded this entire solution. And it fits right into me, and it's extremely effective, right? And at a young age, I was able to code virtually anything, right? And I was really, really comfortable at coding. You could just give me any hard problem, I could just code it right away. And that helped me in competitions, that helped me in like writing a paper. Like I don't, it's embarrassing to even say a paper because it's like I don't know, it's focused on high schools, not really like graduate level papers. So, but I did make it, right? And it was great. So that's the whole idea, right? So now as you do that, you have to reflect, okay? So as you solve this problem, as you learn the background knowledge needed, you have to reflect and say, so what did I learn? Like, what are some motifs, patterns, and themes? Okay, so what are some motifs, themes, patterns I see in knowledge? I see when I learn these types of knowledge, and when I try to solve this problem, when I try to connect two different types of knowledge into one, what are some patterns and commonalities, themes that I see in knowledge? And your job is to generalize. Your job is to make a framework, okay, like a mold that will fit to any type of problem that is similar to that, okay? And the more, you know what a MacGyver's knife is, right? A Swiss Army knife. A Swiss Army knife is a mold that can do anything, right? You just switch to like a tool and then you're just done, right? You got to make your own Swiss Army knife in knowledge, all right? That mold that you can apply to any type of problem, and it will basically help you out a ton. You got to figure that out. You got to make your own mold. And that's what I call a framework. And eventually, if you have many molds, these molds connect with one another. It's like a web of knowledge. It's like a web of frameworks. It's like a web of molds. And that builds your entire framework of knowledge. And this is very different from memorizing. So this is completely not memorization. It's not memorization at all. It's understanding how the world works. It's understanding the inner workings of nature. And that's what you're learning about. It's learning about the framework and the pattern itself, not necessarily like, a squared plus b squared is equal to c squared. It's not like that. When you learn frameworks, if you forget about, for example, in math, if you forget about formulas, you should be able to derive that formula at the start. Okay? Like, you don't have to memorize formulas. If you know the framework of coding, you don't have to memorize code. You can just code it, right? And that's so powerful, because then you can apply what you learned into new things, right? And start doing that, okay, instead of memorizing. Because when you memorize, it's only effective for that specific problem. Like, you can't apply whatever you worked on in a new set of problems, right? It's not going to work. And so that's very bad for you. And it's a waste of time. And you're going to struggle versus if you started learning about the framework of knowledge and you build your own framework. Now, how do we do that? How do we develop this framework? How do we search for patterns? Now we know how to we know that we have to search for patterns. We know that we have to search for motifs and themes. Exactly how do we do that? And the idea is focus on simple things, right? Fundamentals. And this is where I'm going to introduce you bottom up and top down approach. Okay, so there's a bottom up and a top down approach. This is related with coding, design choices. Think of it as a pyramid. And bottom up is starting from the bottom and then you're going up. Top down is starting from the top and then you're going down. Okay? That's bottom up and top down. Pretty easy. And the bottom is like the simplest form of facts. You could say the sky is blue. That's very simple. But, in the face of logics, the sky is blue is even a very complicated, it's even a very high tier and complicated fact. It's like around here. Because, think about it. Why is the sky blue? What is the inner workings of why the sky is blue? Well, I don't know. It emits blue light. Well, why does it emit blue light? What part in the sky emits blue light? And what is blue light? Well, I don't know. And then you just keep on going down, right? Well, blue light is part of the spectrum, right? And it's like that specific light wave in blue lights. Well, why does it only emit that blue light and not emit any other type of color? Like, what happens to that color? Well, I guess that color goes away for some reason. Well, why does it go away? Well, could it be refraction? Well, what is refraction, right? Well, it's where light bends, how light bends, right? In the face of air, water, or even solid like glass. It depends on the density. Well, then why does it only refract blue light? Like, is it refraction or is it reflection? Like, for example, the ocean being blue. Well, why is the ocean blue? Well, could it be refraction? Could it be the density of water, right? And then you can just keep on doing that, and eventually you're gonna get into like the most fundamental forms of knowledge. Like we talked about it, right? Refraction. You could also think about a phenomenon called Snell's law. But then, why Snell's law? Like, why does nature obey Snell's law, right? Well, then, you can think about a more overarching and fundamental framework, like what could there be? Then we talk about the philosophy of nature, like, how does nature behave? What does nature prefer? And you will finally think about the law of least action, or the principle of least action. Nature prefers simplicity. Nature prefers the least amount of action. So based on that idea, light behaves that way too. So therefore, you get Snell's law if you work the math upward. And once you get Snell's law, you get refraction. And once you get refraction, you get the color. And once you get the color, you'll know why the sky is blue. And so on and so forth. Right? So the sky is blue is not the simplest form of knowledge. Maybe the simplest form of knowledge is, in computer science, binary. What is true and what is true is true. What is true and what is false should be false. Because what and means is you need to make sure that both of them should be true. So if either of them are not true, then it is false, right? So those are probably one of the simplest forms of knowledge. You can also think about 1 + 1 is equal to 2. This is also, in our standards, probably the simplest form of knowledge. But all of this is debatable. What many and most mathematicians agree that is the simplest form of facts is from Euclid's Elements. And Euclid talks about axioms. And axioms are facts that we all should believe are true. And it's not a debate about whether if it's true or not. It's not a debate about proving whether if that's true or not. It's like the most simplest form of fact that we should all agree upon. Okay, it's like a belief. It's like religion. It's like you're believing that this is true. And the debate on whether if it is or whether if it is not true is out of the question. That's not a topic to discuss when it comes to axioms, because axiom is a pact. It's an agreement that, hey, whatever it is, we should all agree that these are true, right? For example, a point is a position in space, and a line is a series of points, and the surface, or a plane or a shape, a 2D shape, is a enclosed set of lines. And there are many other things like angles and all that, right? So Euclid's Elements talks a lot about geometry, because geometry is the fundamental description about our three-dimensional world, right? Our three-dimensional world has a point, a line, surfaces, and many, many more, right? You can also talk about distance, and that derives from axioms, okay? So those things, right? So let's go back and talk about bottom-up and top-down approach, and how and why is that effective when you're discovering frameworks of knowledge. Well, the core is you have to break down knowledge concepts into their simplest forms. And the process of breaking down is what? Top down. What about bottom up? Well, bottom up is when you use the simplest form of knowledge or facts that you know and build it up to the knowledge or concept that you're learning about, and that's bottom up. Right? You have to do either. Both is best, right? You have to do either of those. And most of the time, you will be relying a lot on top-down, because, a lot of knowledge is about, well, this is a concept, right? And this concept is an artifact of all of the other building blocks that originate from the simplest forms of knowledge, right? And as human civilization progresses, we will heavily rely on top-down approaches, and most likely forget about the simplest form of knowledge. Just ignore and just say, okay, look, I'm just going to focus on the top-down areas. Now, the reason is human civilization is a pyramid, all right? The knowledge of humanity is literally a pyramid. You started with extremely, extremely simple ideas, that originated from 4,000 BC. And as time went on, several smart people started combining these small amounts of knowledge into slightly bigger knowledge. And smarter people came up with bigger types of knowledge, more complicated types of knowledge. And then, human civilization keeps on stacking this up into like a point, right? And along the way, people do discover some interesting fundamental types of knowledge, but most of the time, human civilization is focusing on building more complicated things, learning about more complicated relationships, because throughout human history, this widening of knowledge, many of them did that, right? Especially during the Renaissance, especially during the Greeks, right? Many of them did that, and there's not much left to do. So the only way to go is up, and that is basically stacking these complicated forms of knowledge these simplest forms of knowledge into more complicated forms of knowledge. And the depth from the most state-of-the-art, this is state-of-the-art, into the most fundamental forms of knowledge, the depth is, the height is pretty steep. It's pretty high, right? And to basically break the state-of-the-art knowledge down into the most simplest parts of human knowledge, it's very time-consuming. The height is especially proportional to time. And we're mortal, we don't have a lot of time, so most people just cut it off. Most people just cut it and say, okay, look, all right, well, I don't have a lot of time. At least I know up till here. I don't want to go down here, right? I just want to focus on these. Most people do that. The deeper you go, the more adept you are at human knowledge. The better you will be at understanding this concept. Okay? So that is why at the beginning, I talked about you should have all the time in the world and try to dig as deep as possible. Because what happens is you get compounded returns as you do that. It's not like, let's say I have 100 things to learn and every time is like extremely time consuming. Do I have to repeat that every single time for 100 times? That's not really the truth. The truth is that you get compounded returns because it's exponential, all right? You get growth because if you dig a single concept very, very deep, you will learn a ton of fundamental knowledge. Okay? You'll learn a ton of frameworks, a ton of molds. And using those molds at the second iteration, it gets a lot easier because the second form of knowledge will be extremely connected to the first knowledge along the way. You already know that, right? And basically, solving the second concept will be a lot easier than the first, and so on and so forth. And so, the amount of time that is needed to learn 100 concepts decreases exponentially. The first concept that you learn will take a lot of time, but the deeper you go, the steeper this curve will look like. So if you learn extremely shallow, this is what the curve will look like, right? If you learn extremely deep, this is what the curve will look like, right? So these are people who love learning, and these are people who hate learning. Okay? This is why people take a very, very long time to progress, succeed in life, if they hate learning, because it takes so much time to learn. Now, this is what? This graph is about time. Now let's translate that to progress. Okay, let's translate that to progress and see. Well, I bet you know. So this is people who hate learning, and the blue is people who love learning, right? And there comes a point in life where, the blue guys dominate the red guys. Okay? Now, I unintentionally color-coded correctly. Blue means slow learning. You have all the time in the world. Red means fast learning. You don't have all the time in the world, and you just learn everything shallow. You got to be a slow learner, therefore. Okay? That's what I'm trying to say. So to review, you have to keep on digging to break. You got to keep on breaking down this concept that you know, that you learn, into simpler and simpler and simpler and simpler concepts until you reach the very end, where you reach an axiom or where you reach like some knowledge that you already know, right? That is the habit that you have to take. And as you're doing that, well, obviously, you're going to do a ton of research, right? As you keep on going down, you need to know how to get down there, right? And basically, that's backtracking human knowledge. That's tracking the history of human knowledge. Like, who discovered this? Why did they discover this? Well, then you're going to look at the past, right? For example, like, how did Albert Einstein figure out, well, general relativity? Well, I don't know. You got to look at Newton, Isaac Newton. Well, how did Isaac Newton figure all of these out? Well, you got to look at Galileo Galilei, right? Who invented calculus? Well, both Newton and Leibniz, right? And like, why did they do that? Well, there was an ongoing discussion about infinitesimal changes before or during the time of Isaac Newton and Leibniz. And, they're the ones who kind of build upon that. You know, and so on and so forth, right? There's like a whole trail of people who figured these stuffs out because of predecessors and predecessors and predecessors, and they all boil down, well, into Greek philosophers like Euclid, Archimedes, Socrates, Aristotle, right? All of those guys, right? And that's why the Greeks are still talked about today in world history, because they're so influential on their philosophies, that reach up till today. Like, they're the ones who basically made our current idea or foundation of mathematics and science, right? And basically that's the whole idea, right? The reason why you're researching a ton is because you need to track down that entire history. And as you track down the entire history, you get to appreciate and learn a lot about how they thought about the problem, how they approached the problem, what's the current history of people approaching these sets of problems, and so on and so forth. And then you can learn from the shoulders of giants, right? So it basically piles up, right? So that's how you do it, right? So again, to review, you're breaking things down into simpler and simpler concepts, and it's great to also use bottom up. As you review, you can review by starting from the most simplest types of concepts and just build your way up. As you review, build your way up by yourself without referring to any type of book, and build yourself up to the knowledge that you are learning right now. And once you do that successfully without any help, you can say that I've successfully mastered this concept because, well, I basically memorized the entire trajectory on how to develop that concept from the very beginning, right? So while doing that, you should have been able to memorize the framework. You should have been able to memorize the whole schematics of the knowledge or the concept that you learned. Now, I'm going to transition to the tips and tricks to learn effectively, and this is all connected. Now, in order to obviously track the entire trajectory, right, of knowledge, you can't just do that orally, like how the Aboriginals did. Like, it's impossible to do that. Why? Because it's so much. You got to be like a mentat from Dune in order to do that. It's not efficient. It's not effective, right? An easier solution is to write notes. Okay? When I studied on my own, I used to write like whole novels, whole books, okay, of notes while learning math, physics, chemistry, all the high school texts and all the college and grad school ideas and papers, I used to write a lot, and I do write a lot. I am buried in writing, and I have to write a lot more. The reason is writing notes is like you're you're basically writing your memory into something permanent. This leads you to have infinite amount of memory. You don't have to stress your brain and memorizing, recalling like the concept or thought that you thought about hours ago or days ago. You don't have to do that. Just write it down on a piece of paper, and if you want to recall, just flip the page and read the words that you wrote before, right? That's the power of writing notes. It gives you like a whole storage of permanent memory that you can recall at any point in time, and that will give you a significant edge. And common sense, right? That you really, really need to write notes in order to digest this huge, long history of people, finding and searching like knowledge. Because, part of the superpower of learning is you get to digest these geniuses, right? The whole life's work of these geniuses, right? You get to just like digest the life's work of Einstein, the life's work of Newton, the life's work of like Lagrange, right? Or Euler or Euclid, right? You get to digest that in a single sitting. You get to really understand their thought process, right? That they have struggled to figure out for years. And what they did was, as a service to humanity, they literally wrote their thought processes in a sheet of paper. And now we can read that and just easily download that information, right, that they thought about into our brains. And therefore, we get to be the same caliber in knowledge as them. We get to digest a lot of that, right? And that's that superpower. We get to be geniuses. We have like years of knowledge that geniuses have paved the road for us. And using that knowledge, we get to develop something that is way cooler, way better, that Euler never have imagined or Einstein never have imagined before. That's what we need to do when it comes to learning. But sadly, in 2024, or at the end of 2024, fewer and fewer and fewer people are doing that because, well, I guess short form content, pressed for time, information grows exponentially, whereas our life expectancy increases linearly. Maybe that's why. We have a lot of other stuff to do, but you're selling yourself short, okay? So that's not great. So, okay, in common sense wise, you got to write, okay? And you got to make a habit of it. And the art of writing is a skill that you can learn on your own. Just try to write fewer words with greater impact and greater meaning, okay? That's how you can condense your writing. For example, I can write your memory into permanent storage. Okay, so I can say like, you can possibly, maybe, if not, I don't know, it's like an example, write your, what do you call that? Like recollection of thought. This is what? Wordy. It's uncompressed. You can just write it like this, whereas you can just write it as long as that. Make your words simple, right? Write your words in like fewer, okay? Just write simple, because when you look back, you have to be able to read your writing faster, right? That's the whole point of writing. If it takes extremely long for you to recall your memory by reading that thing you wrote, it's inefficient, as opposed to like if you can read that in like 2 seconds and immediately recall like what you thought about. That's way better, right? It's going to save you a ton of time. So you got to learn how to write simple and effective, compressed, right? It's about efficiency. So you got to do that, okay? So simple writing. And practice that skill. Learn from the greats. Learn from Hemingway. That's who I know, right? Hemingway writes real simple. Catcher in the Rye. Well, the main character is a high school kid. The author intended to write really, really simple, right? But he conveys a ton of meaning. That's great, right? So read Hemingway, read Catcher in the Rye, or read all the simple words that authors use to convey meaning. Don't be wordy. Also, writing, get your hands active. Okay? It's always better to use your body, use your mouth, use your hands to get dirty in learning. And that's always, always effective. Okay? And another lesson to be learned is learning is not all about the brain. And this is from biology. Our neural system, or our neural system, which also includes thought, brain, emotions, feelings, sensory, signals, right, whatever, right? That is scattered all across the body, all right? And a lot of evidence, modern evidence, suggests that thinking does not simply originate from the brain. It's scattered across all in our body. Because, number one, there is an IQ of 120 person who doesn't have a brain, who has an empty skull, basically, and this guy functions normally. Another type of evidence is people who undergo organ transplants adopt the donor's personality. So a woman who, had like a donor's liver suddenly became really aggressive, suddenly became more male-like because the donor was a guy. And also she inherited the guy's personal traits, right? Heart donors also, have experienced those types of cases. And, you can look it up. There are a lot of cases like that. And we slowly start to think that the neurons in the organ contributes to someone's personality, someone's way of thought. And this is like a telltale sign that thinking doesn't really originate from the brain. When you feel things, when you think about something, you try to wave your hands, right? You try to use hand signatures. You try to talk. If you run after hours of thinking and you just can't solve this problem, if you run, you suddenly get a eureka idea. If you have a nice warm bath, you suddenly get this revelation on some new idea that you have, right? All that stuff suggests that you got to use a lot of your body to generate original, high-quality thought. And don't be afraid to use that. So what I do, although this is slightly embarrassing, but I'm proud to say it, I talk to myself loudly whenever I learn, okay? I have this large chalkboard in my room, and I'm going to talk about this soon. I write stuff, okay, as if I'm doing a lecture, a one-by-one lecture, one-on-one lecture on these concepts. And I speak out loud, and I role play like the teacher and the student both. So as a teacher, I explain things, and as a student, I immediately switch tonality, and I ask questions. I pose as I act like as a devil's advocate, and go like, okay, why is this the case? Why is that the case? Can you explain this? Can you explain that? Right? And I immediately switch to my teacher mode, and then I kind of explain that. And I constantly debate to myself, and my parents comment that they're scared of me doing that because they were okay when I was a child. Children, they do that. But even when I'm like a grown-ass man, I'm just keep on doing that. They are worried that I have schizophrenia or like some kind of split personality. And I'm like, well, this is how I perform. This is how I learn, right? But, I'm comfortable doing that. And I sometimes scream at myself, and it freaks my mom out because now I'm a grown-ass man and I'm keep on doing that. Like, she's seriously worried that I have schizophrenia. But I'm constantly reminding her that I don't. It's like my mantra. It's like my second self when I learn. And that's really great for me because I get to digest extremely difficult content that I will never be able to imagine to achieve without this role play. If I just sit tight and think to myself alone, it's never gonna work. I won't understand. It's not gonna gel with me. And how does that connect to writing notes? Well, you're using your hands. You're actively learning, right? Part of learning is being active about it. And using your hands gets to build you that habit of using your body, using like a lot of other things except the brain to get the whole blood flowing, to get those ideas flowing. And that's why I encourage you guys all to write. Now, let's talk about teaching, the role play of teaching and student. I used to do this instinctively. It was my talent. I didn't learn from anyone. So I'm lucky, but when I was like a teenager, I kind of researched that, whether if I'm normal or not. And certainly it was normal, and it's a very effective technique to learn. It's called Feynman's technique. The whole role play is Feynman's technique. Feynman adds on to the teaching and the student behavior. He adds to explain things as simple as possible. Okay, so he would walk across town, tap on an old woman's shoulder, and try to ask questions about quantum physics, like all the difficult things that he'd been working on, and the grandma would reply really, really clever answers to Feynman. Now, it's not that the grandma was a genius. It's more about the fact that Feynman explained extremely difficult concepts like quantum mechanics and physics in a way that the grandma would completely understand the crux of the problem. And Feynman would do that whenever he was stuck. He would just ask children, old women, old men, right? Just, I don't know, people who are farmers who just have no clue about what quantum mechanics even is, who has no recollection on delving deep on math. And they would give Feynman really, really clever answers, really out-of-the-box thinking answers that Feynman would use in his formulas and his techniques. He would, I don't know whether if he did it by himself, I forgot, but that's a famous story. You can do that by performing the teacher-student role play. The student should be like a 5-year-old, a very naive child who has no idea about the world, but has some idea of common sense. So that child is a smart child. He knows about the inner workings of knowledge. He knows about the ways of nature. He knows which explanation makes sense and which explanation does not make sense and is convoluted and all of that. The teacher's role is to explain to that student about a very, very complicated concept. And the student will naturally ask the teacher, why? How? What is that, right? The student's going to force the teacher to break knowledge down into simpler and simpler and simpler ideas until it is so simple that the student will be forced to accept and acknowledge that idea and determine it as sound and truthful. And that's the whole idea of Feynman's technique. And as we practice that skill, the teacher will get better and better and better at those things. The teacher would directly explain an extremely difficult concept into simple terms, right? And as you keep on doing that, as you keep on practicing that, you get better at that. And eventually, you will be able to understand an extremely complicated subject in a very simple and intuitive way. And that's a great plus because you can learn even harder and even more challenging concepts at ease, right? So that's Feynman's technique. So make sure we practice that. Now let's connect, finally, let's connect AI, state-of-the-art AI research, and how this contributes or how this supports Feynman's technique. And an AI, well, it's like the chicken or the egg, but it's defined, like we use Feynman's technique in AI research a lot. And right now it's at its infancy, okay? And obviously, if there are some grad students who are listening to this, here's a great hint. I don't know how this will go, but it's a great idea. We have not successfully applied Feynman's technique in direct AI training, okay? We kind of have an idea. There are some mathematical formulas and training algorithms that touch upon Feynman's technique, but it's not really Feynman's technique. And one of the things is self-distillation. Be your own teacher. There's that paper about it. There's adversarial training. Adversarial training often leads to generalization. There's also the explainer and the listener framework that DeepMind, or was it Microsoft, what they published in order to reach stage 2 thinking. Was it stage 2 or phase 2 thinking? I don't know. And what they all do is you split an AI agent into 2 roles. The first role is trying to learn about the data. It's like the whole student. And the other is trying to evaluate whether if that learning is great or not. And by doing that, both of them learn from each other. Well, when it comes to self-distillation, there's only one guy who learns from it. So if there's a student and a teacher, the student learns about a concept, okay? This is the AI model. And what happens is the student updates its current state of knowledge to the teacher continuously, all right? And the teacher is simply an average of all students' progress. Okay, so the student will learn this and that, concept A and B, throughout time, whereas the teacher is going to understand, the teacher will be a simple average of all of the progress that the student has learned. And what happens here is that the teacher gives knowledge to the student. The teacher says, okay, look, both feed the same data. And the teacher goes, okay, look, I think from all of the things you learned, I think the response or the actual output from that data should be this. And the student not only learns from the raw data, from the raw labels meaning what you should learn. So for example, if the data is the image of a cat, the label would be what? Well, the student should classify this image as a cat, so the label would be a cat. the teacher goes, okay, look, I think the data is somewhere in between a cat and somewhere in between a dog. All right? You got to learn from that. The label simply suggests that it is 100% cat and 0% dog because, well, the label only talks about cold, hard facts on what this data is. So the student gets to learn from both perspectives. Okay, say, okay, look, yeah, I know that's 100% cat, but I also want to learn that it is half cat and half dog, right? And as the student learns from that teacher, which is what? The teacher is simply a reflection of its own self. The student gets to perform a lot better than not doing this, okay? And this is also like this idea of self-learning and how you can split your role by yourself from being a student and a teacher at the same time. You're distilling knowledge that you have learned by using, well, partly Feynman's technique, but obviously in mathematical in sense, like it's slightly different than Feynman's technique. You also have this idea of explainer and listener, where the same AI model, a large language model like ChatGPT, explains a concept, and then you toss that response to the listener, and the listener, I forgot about it, but I think the listener like gives comments about like to the explainer on like guiding that explainer on like what you should do, what you should correct, and all that, and the explainer keeps on going, and as time goes on, you would get a more refined and deep response about the problem at hand, about like the thing that it needs to respond to. And this is also like this whole split personality idea where even though the AI model is the same, by splitting roles, you get to have an interplay. And therefore, you get to refine your initial thought process, your initial knowledge, and get a more mature and refined answer. So all of these lead to the fact that, you know, using AI, using Feynman's technique in AI training does, in fact, significantly improve AI models. Now, although the video is getting much longer than I expected, let me just see if it's recording. Still recording. We got about 2 more tips to look into, and that is when you're trying to make a framework about the world or the knowledge, there are many frameworks that you can develop, right? Starting from a very complicated framework, but, you know, when you validate that framework in your current span of knowledge, it works. You can also have a very simple framework that also works. So they're all true. They all fit to your current perspective or your current knowledge database. What should you choose? What framework should you choose? Should you choose the complicated framework or should you choose like the simplest framework? And the answer to that is simple is best. You have to choose the simplest framework. So as you develop your own framework of knowledge, you should be able to, you should try to make your framework as simple as possible. Your mold should be really simple, right? Very predictable, very simple. So instead of making a star-shaped mold, you should strive to make a square-shaped mold or a round circular mold, right? Like the mold should be really simple, and you should strive to do that. Make it simpler and simpler and simpler and simpler. And naturally, if you go through Feynman's technique and all the things that we talked about before, you will get a simple framework. But why? Why do we need simple frameworks? And the idea to that is, well, that's how nature behaves. Nature behaves like that. Nature likes simplicity, favors simplicity. And this is the law of least action. And this is clearly said in the latest video of Veritasium, based on this recording. Basically, all of the equations that we know about the universe, F is equal to mass times acceleration, or Einstein's general relativity, it all boils down from the law of least action. So if you compute physics based on the perspective that nature favors the least amount of energy that you consume at every given point in actions. So imagine like the universe or motion is quantized, meaning like you have chess, like it's like a chessboard, right? And you got a single point and you can make decisions to go from here or here, right? So it's quantized, you can like choose only one thing. It's like a video game, like an 8-bit video game. You gotta choose the way, you gotta make a decision that promotes the least amount of action from going to point A to point B. Well, I guess then it's right here, right? So it's like a chessboard, and imagine this chessboard being smaller and smaller and smaller and smaller and smaller, like infinitely smaller, and ultimately you get what? Like it's close to a continuum. It's like continuous space. So if you want to go here, like which trajectory should you take to promote the least amount of action, right? Well, that ultimately equals, and that's what Veritasium explains it, I haven't delved deep into it, but that equals force is equal to ma if you want to like, derive that entire math framework into like a single formula. So it basically translates into like those equations that we commonly know and accept as universal truths that show how the universe works and behaves. So this also aligns close to Occam's razor. Occam's razor says if you're forced to choose between the complicated solution and the simple solution, and both of these solutions are correct, for this specific type of problem, it's best to choose the simplest solution because the simplest solution often generalizes better into other types of problems, and the complicated solution does not. It also translates to AI. We use dropout, regularization, typically weight decay. We even think about sharpness aware minimization. And all of these promote simplicity. Imagine AI trying to fit points. There's one AI that fits like this. There's another AI that fits like this. Which is simpler? Well, it's this, right? This is a lot simpler than the blue one. Why? Well, it's because you take the least amount of action, right? It's straighter, it's smoother, right? Versus like all of this, you have like so much, curvature in your like solution. And oftentimes this performs worse because this is what we say as overfit. You have too much curvature, you have too much complexity. You have too much sharpness in your entire solution. Whereas in here, this is good. It's smooth, right? And if there's any variation, that's the key word, and that really, really connects to the law of least action. There's not a lot of variation. And for here, this has a lot of variation. And what does it mean when it comes to variation? Variation means, say you have a model, all right, an AI model, and you feed the data and you kind of perturb the data with like a very small amount of value, right? Maybe like 0.0001, right? Or something like that. Some kind of small value called epsilon. And you put that in, you use the same model, and you put the data in there, right? What is the output? So there's y1 and y2. Well, if you do that many times, right, you should say that y1, the difference between y1 and y2 is around some value, right? Actually, I should say delta change, right? Whereas you have another solution that is another type of delta. If this is smaller than the red delta, we should say what? Well, the difference between this and a very small change of input data with this should be, well, smaller, right? Because there's not a lot of change. And the model does say that there's not a lot of change. But if you're on the red side, like a super small change suddenly changes the entire solution drastically. And that means what? You have more variance, right? More variance. Right? And there's less variance. Which is robust? Which is more reliable? Which is more trustworthy? Well, obviously the white guy, right? Because it's not sensitive. It's not sensitive to that small amount of change. Like, for example, let's say you have an image of a cat. If I just add like a grain of pixel in here, if it's very sensitive, suddenly it classifies into like a boat or a frog. I don't want that. I want it to be as a cat. That's the whole idea of promoting least variance. Okay? And when it comes to least variance, in the phase of this theory called sharpness-aware minimization, which DeepMind also published, least variance equals flatness in the error curve. Now imagine that. Well, why is flatness the thing? Well, think about this and this, okay? So which is flatter? Obviously this one. I'm going to color code this so that it's easier to recognize, okay? Which is flatter? Well, obviously this, right? Well, why is it flatter? Well, it's flatter, right? Literally, if you just see it, right? Now, what does it mean to be flat? If I have a data point right here, and if I change some small value, right? And when we look at the y-axis, is there a difference between this and this? Is there a difference? Not much. What about this and this? So the difference between this, the blue one, the blue point, and the red point. There's not a lot of difference in the flat one, right? But just gonna do yellow. But what about this? Is there a difference? If we shift it small to epsilon, and we shift it small to negative epsilon. Yeah, there's like a lot of difference, right? The difference is like this much, whereas the difference between here and here is like, I can't even draw it. It's like super small, right? So what SAM, sharpness-aware minimization, does is, well, look, let's try and find a solution that promotes flatter error curves versus sharper error curves. And this is why they call it a sharpness-aware minimization. We're aware of our solutions getting sharp, and we exactly want to avoid that. That's what AI does. And all of these, right, all of these types of regularization, they all promote to say, we want to minimize variance in our solution. We want to minimize variance in our understanding. So whatever change in input, whatever change in data we want to make, we still want to be robust in that solution. All right? And that is close to choosing simpler solutions, because simple frameworks promote least variance. Because, well, let's say you got like because simpler frameworks are insensitive to small changes in concepts, right? So for example, I cannot think of an example, sorry, but you can think of it as an example of basically complicated frameworks depend on a lot of variables. This depends on few variables, right? And if you depend a lot of variables, right, then by the curse of dimensionality or the curse of high dimensions, a very small change, right, can lead to drastic changes in high dimension space, right? Because, well, think about it, right? Like there's a higher probability, right? So let's say you got, 100 variables. Let's say that there is a small change in idea. Well, what is the probability of changing at least one variable in 100 variables? Versus you got two variables. What is the probability of at least one variable changing out of two variables, right? Well, the probability of this is much larger than this, right? And you can calculate that using binomial theorem. But that's the whole idea. All right, now on to the last tip, and this is slightly cool. This is very cool, and this could be a great reward to people who have listened to this lecture up till the end. So congratulations, everyone who made it this far. On to our last tip, the 85-15 rule. The 85-15 rule is, I think, a very new discovery. It's published in Nature, I think like a couple of years ago. They said they experimented on machine learning, right, AI algorithms, and also I think on animals too. And they did a bunch of tests on like so many different types of mediums, meaning like AI, animals, humans, whatever, right? So after they did those experiments, they all came to the conclusion that learning a subject where 85% of the content, roughly 85% of the content, you already know. It's easy. You're used to it, you know, right? You're already comfortable with this concept. And 15% of the content in the subject is hard. You do not know. You're not comfortable with this, right? It's something new. Like it's actually challenging for you to figure out. If you maintain this ratio, it equates to the fastest learning. It equates to fastest learning, theoretically and both empirically. So what that means is you should not challenge yourself too much. You should not only work on super easy problems. You should have a healthy balance between the two, and typically that balance, that ratio among like the easy concept versus the hard concept should be 85% and 15%. So make sure that you kind of like, balance that thing out. So maybe, let's say you want to learn calculus, but you don't know pre-algebra. Well, you should not do that. You should not just, hit your head against a wall just by trying to learn calculus without knowing pre-algebra, because that means that most of the content that you need to learn about calculus, you have no idea, and it's very challenging for you because you didn't learn this. So it's best to learn a curriculum, right? It's best to learn step by step, slowly but surely. Now this also relates to AI as well. AI has this idea called curriculum learning. You basically teach the AI starting from really simple ideas, and you slowly refine that. You kind of ramp up the problem harder and harder and harder, so that the AI kind of learns step by step. And if you do that, the AI successfully learns, and it generalizes really, really well. It learns, it's able to solve problems that it has never seen before related to that domain pretty effectively. But if you do not perform curriculum learning, the AI just does not learn at all. It just learns a very, very difficult or very, very ineffective pattern where it's just rubbish. It just doesn't learn at all. And it's impossible to learn at all, despite fitting like a bunch of these techniques, fitting like a bunch of different training techniques, fitting a bunch of like large models, complicated models, whatever. It just cannot learn, right? And this is really the case in the face of reinforcement learning, right? So we usually go with imitation learning, where we kind of, learn from human demonstration, and then we let the AI just take over and say, you know what, now that you learned how the human does, how the human functions, just be better than that. And that's another example of curriculum learning, right? You learn from the best, and then you kind of adapt to that. There's also, what was that? From Uber, Go to, I'm not sure, Go to learning, where they it's very hard to explain in simple terms, but when you're traveling like a maze from point A to point B, and the problem's really hard, you kind of like brute force in solving the maze first, grab some lessons learned from the brute force that you learned, and teach the model from that. So it's basically like, at least find a solution and how to solve this complicated maze, and then extract the lessons learned from that brute force endeavor, and then you teach the model from that. And then as the model gets better, you slowly, take your hands off the wheel. You kind of like let the model learn on its own, slowly but surely. And that's like what the Uber paper did. And basically it's like, you know what, I don't really care about how the AI solves it. I'm just going to brute force my way through. And it's like substituting at every position, right, in the maze. Well, Uber did it in a more clever way so that it conserves data. But they kind of did that in a clever way. We kind of brute forced it in a clever way and figured out how to solve this extremely complicated problem, right? And they taught the model how to solve that problem through like demonstration, right, from the brute force solution. And they kind of let the model do it on its own, right? And say, okay, look, now that you learned how to do this, just solve it on your own based on the results that we provided you. And it slowly does that in a curriculum way, right? And it kind of actually solves that extremely complicated problem, whereas none of the other AI models, no matter how complex and no matter how clever the training techniques were, they all failed miserably at even attempting to solve that problem, let alone solve that problem at the fastest time or trying to speed run that problem. So this is the importance of trying to work your way through by tackling easy problems and work on solving hard problems intermittently, or like in this type of ratio where 85% is easy and the 15% is technically hard. Okay, So if you abide that rule, I think you're going to learn really, really fast. So that's it as a lesson. I guess as a last bit, never have ego when you're learning. Always test your knowledge by doing practice tests, talking with like-minded peers, your teacher, mentor, whoever it is. I know this is part of self-learning, but the whole idea of self-learning is a very singular technique. It's like a very myopic technique that is very effective in your life, but it's not everything. That should not define your entire learning career, let alone your life. You shouldn't be alone, right? But as you get better at self-learning, well, you're going to get better at life because it's a great technique to learn. So make sure you mix a lot of other forms of learning while doing self-learning. For example, talk with people, talk with teachers, right? Debate, discuss, right? Solve practice tests. Sometimes, let alone cheat, right? Let alone memorize some formulas, fake it till you make it. It doesn't really matter as long as you learn, right? And get better at it. And like I said, right, even in AI, there are problems where you really have to feed in brute force solutions to the model before the model gets good at it, right? You too, us too, right? We can't really solve a problem like at the get-go. We can't solve every problem at the get-go. Sometimes you gotta fake it till you make it. And the art of that and the science of it is you gotta learn how to balance that out. And you gotta kind of be honest to yourself. Like, oh, is this a phase where I have to cheat? Is this a phase where I have to look at the cheat sheet? Or is this a phase where I have to look at hints and figure it out? Because not really looking at hints at all is actually a very inefficient form of learning. Maybe you're not following the 85-15 rule. Maybe this problem itself is really, really hard and you really need a hint in order to move forward. So do whatever is necessary to get better at things. But since you have learned all of these techniques that we've talked about, now you have a better sense of how I should learn, right? And what are some of the things that I should be careful and what are some of the things I should note about when I'm actually digging deep into this type of learning. So I hope this video is helpful and, get better at it, all right? Good luck to you all.